All right, today we're going to talk about combinations, which is perfect since this unit is actually on combinations. It's finally nice to get to the thing based on the title of the unit. I'm going to go back and remind you that permutations, order mattered. It mattered which thing we chose first, which thing we chose second, which thing we chose third. With combinations, it does not matter. Order is not important. All that really matters is what you've actually got once you're finished your selection process. Um, so for instance, if I was choosing, I don't know, 3 friends to go with me on a vacation, it doesn't really matter which one I asked first, which one I asked second, and which one I asked third. All that matters is which 3 are actually coming with me. So I'm going to point out that there is some notation to do with this one. 2 of the notations are pretty much exactly the same as they were for permutations. One of them is just a little wee bit different. So this one here is the one that should look familiar. It looks just like our permutation notation, except instead of a P, there's a C. And it's basically saying that the first thing in the bracket, the N, is how many things we have to choose from. And the second thing, R, is the number of things that we're going to choose. So that is actually our preferred notation if we're trying to type information or type math, which we don't often do too much, except sometimes in an online course or if you're a teacher trying to prepare these nasty documents. This one here is the button on your calculator, again, just like the permutation button, except it's for combinations. And this one here is our new notation, and means the exact same thing as the other two notations. The top number is the number of things we have. The bottom number is the number of things we're choosing. I'm going to tell you right now that most people, when they're first learning this notation, have a really hard time not drawing a fraction line between the n and the r. And it's because this is not a fraction, but we're so used to doing that when we have a number over a number. So the notation is just a rounded bracket with the number on the top being the number of things we can choose from and the bottom being the number of things we choose. And if you're wondering why this has a different notation than the permutations, I'm hoping I'll justify that by the time we're about halfway through this lesson. But for now, that's the notation we're going to prefer to use when we're actually doing handwritten answers. So the one that you're going to use and the one that I'm going to use when I'm writing on this document. By the way, if you are good with Microsoft Word or really good with Google Docs, you can make that symbol look like that as well, the bracket with a number over a number. But I'm not going to tell you how to do that. If you can do it, great. If not, use the other notation, the C bracket and comma R bracket. Okay, just a reminder, this is the equation. Well, I shouldn't say a reminder. I guess technically this is the first time we're learning it, although we kind of foreshadowed it back in the permutation unit. That's the definition of a combination. It's n factorial over the difference between n and r factorial times r factorial. Permutations had a very similar notation except no r factorial on the bottom. And that means that a combination is a permutation divided by r factorial. And again, we talked about why this was true back in Unit 2. And it's because this is unscrambling the order of the things that we choose. So the r factorial on the bottom is basically removing the order part to a permutation. So regardless of which notation we use, we read it as n choose r, or in the example that I put right here, we would read that as 6 choose 2, again, regardless of notation, whether it's the first, second, or third version. There's a couple of things here that you should know. The first one is that n choose r is identically equal to n choose n minus r. So if I think about this, n choose r by definition, let me just change to blue here, is n factorial divided by the difference between them, and then times r factorial. So regardless of whether they're variables or letters, because you can use different variables in this, we just usually use n and r. It's the top number factorial divided by the difference of the top and the bottom factorial and the bottom factorial. Now, if we take n choose n minus r things, that's going to be n factorial over, now this is where it gets a little bit confusing. It's n minus r factorial and then n minus r factorial. And if I simplify that a little bit, that first bracket, n minus n, they cancel out. The subtract negative r becomes r factorial. And then the second bracket is n minus r factorial. And I think what you'll see is that these two are identical except for the order of multiplication on the bottom, and order of multiplication really doesn't matter. Now, just as a little bit of further explanation of why this works, I'm going to just pick some numbers to throw in here. So I'm going to say, for instance, 10 choose 3 is the exact same thing as 10 choose 7. And I'm going to just explain quickly why that's true, or why that should be true. Pretend that you have a group of 10 people in front of you. And again, beautiful thing that you could do in this course is actually visualize doing whatever the question is kind of stating, even though there's no context to this one. But pretend there's 10 people in front of you and you have to choose 3 of them to come with you on a trip. Well, that's the exact same thing as choosing which 7 you're going to leave behind. So whether you choose 3 to come or choose 7 to stay, you're still breaking the group into 2, one group of 3, one group of 7. So that's logically why those two things are equal. Mathematically, they're equal because of the definition equation. All right, before we go too much further, I'm going to give you just a moment to think about a few questions here and ask yourself, are these things permutations or combinations? Does the order of my choices matter? This would be a good time to pause the video, try each of these 4 situations, and just write down, do you think it's a permutation or a combination? Do that now, and we'll take these up in about, whenever you're done hitting pause. Okay, the first one, A. You're choosing 2 people to play the leads, Romeo and Juliet, in a play. Does the order matter or not? Now, this is where, again, some people will make the argument that I could choose, someone to play Romeo and then someone to play Juliet, or someone to play Juliet and then someone to play Romeo. That's not really what we mean by order mattering. What we mean is, does the person assigned to Romeo and the person assigned to Juliet matter? Would switching them make a difference? And I think you can agree that regardless of how you're casting your play, if you at the last minute switched who was Romeo and who was Juliet with each other, I think it would be a very different play. So I think this one is going to be a permutation where the order matters. And by the way, I'm just going to use perm quite often just to abbreviate permutation. Now, how about part B? You're choosing 2 people to do lighting for a play. Now in this case, I could choose, let's say, Jim and Susan to be the lighting people. And does it really matter which one of them? Is there a lighting part A and a lighting B? Maybe there is. I'm sure that there's some tech people in the class that are going to yell at me for suggesting that these two things are the same. But I'm going to make the argument that for at least the purposes of mathematics, it doesn't matter. If we switch the 2 lighting people at the last moment, they're still the 2 lighting people. So that would be considered a combination. And we'll abbreviate that one the same way we abbreviated the other. Part C. Microwave dinners are on sale at the supermarket, and a person wants to buy 4 different ones from a selection of 7 types. Permutation or combination? Well, in this case, what I want you to think about is when you leave the supermarket, when you get home and put them in your freezer, does it matter which order you selected them in? I think all that really matters here is which ones you actually left with. So it's a combination because, again, order does not matter. For D, the person who bought the dinners in part D has to serve them to their family of 4. Okay, so picture yourself sitting around a table, 4 people sitting around a table, each with a dinner. Would it make a difference if you switched out who got what? And I would make the argument in many situations it would. For instance, I personally am allergic to fish, so if one of the dinners was fish and it got switched from someone else to me, it would make a very big difference to me. My brother's a vegetarian. If he got switched from pasta to beef, I think he'd be a little offended. So I think the order of the dinners does actually matter, despite the fact like what doesn't matter is the order they get put on the table. Like that, in that sense, the order doesn't matter, or who is handed their dinner first. What does matter is who is assigned to which. So that would be a permutation. Okay, so this is going to be an important thing when we're kind of moving away from this unit. I mean, this unit, it's still important to understand a permutation versus a combination, but of course our focus is on combinations, so you can probably guess in most situations which one you're going to use. However, as we move into probability and probability distributions, we need to start recognizing in questions what approach to take. Do we approach this as a permutation or do we approach it as a combination? And many will be obvious. You'll kind of see them almost immediately, and some you're going to have to think about. So let's try some actual problems. Now this first one we actually have covered before back in the permutations unit by modifying the question a little bit and fixing it manually, but we can now do it much quicker and much easier by using a combination. So how many different combinations of numbers are there in Lotto 649? And 649 is called that because it's 49 different numbers and you choose 6 of them and you have to match the ones that are chosen by the Lotto people in order to win. So now this one's a pretty straightforward combination. It's literally just 49, choose 6. Okay, and all we have to do is find our combinations button on our calculator. If you found your permutations button last unit, chances are the combinations button is beside it or very close to it. So I'm going to type in 49, choose 6. And I get out, I believe, 13,983,816. Okay, so that's quite a few possible options. So winning this is approximately, like winning all 6 numbers or matching all 6 numbers is about a 1 in 14 million chance. So the good news is if you play the lottery every week, you'd only have to play around 14 million weeks before you're likely to win. 14 million weeks. That's that's 269,000 years. Yeah, I don't think any of us is going to be around in 269,000 years. So if you choose the lottery, please do so assuming that your money is just going away and never coming back again. If you can't afford that, don't do it. Lotteries are not a source of income to replace actual jobs that you work at. Just a public service announcement there. All right, part B. Super 7 is a different lottery. If we gave it the same kind of name, we could call it a 747, but that's already the name of a jet, so they probably didn't want to use that. But it's the same idea as the 649, except there are 47 numbers. You get to choose 7 numbers to win. And how many ways could we choose the correct numbers in this lottery? So before we actually figure out what the answer is, before we type it into our calculators, I'll write down this part because I think it's obvious. It's 47, choose 7. I want you to ask yourself, do you think that this is going to be a bigger number than the 14 million or a smaller number? Is this lottery going to be easier to win or harder to win? You have to keep in mind that anyone who runs a casino or a lottery or any kind of game like that where they're trying to make money, they're always going to make things or make games in a way that make you feel like you've got a good chance of winning, even if you don't have a good chance of winning. So in this case, the logic behind coming up with the 7 out of 47 numbers was they're trying to push the idea that, well, not only do you have less numbers to choose from, you get to choose more numbers. How could you not win? And the answer is really, well, but I have to now match 7 instead of 6, which is harder to do. So even though I've got 2 less numbers that it could be, I've got 7 I need to match instead of 6, which is sounds to me a little less likely. So I think there's going to be more ways that we could do this, but let's see what the math says. So pull out the calculator, type in 47, choose 7, and I get, oh yeah, there we go, 62,891,499. Okay, so your odds of winning this are about 4 times less than they are for winning the Lotto 649, at least for matching the grand prize, which is why the grand prize on this one's actually higher, or at least normally is. Prize amounts often vary based on how long it's been since the last prize was won. Okay, so which lottery are you more likely to win? 649, by a factor of about 4 and a bit. Okay, so the good news is we're only doing like 3 examples today. The bad news is part 2 has got like 14 parts to it or something like that. Actually, I forget how many it has, but it has a lot. But we're going to keep with a common context so we don't have to keep memorizing new things. And we're going to basically see a whole bunch of different scenarios about how things can play out with combinations. Okay, so for all of these part 2 questions, or number 2 questions, we're going to deal with a group consisting of 15 elementary students, 11 high school students, 12 post-secondary students, and we want to choose a committee of 5 from that group to look at the new curriculum. Um, Before we go any further, I do want to emphasize that just because I've said 15 elementary, they're not the same. They're not identical or repeated or duplicate objects. They are individual people. They just all fall under the category of being elementary students. Okay, that said, yeah, the high school and post-secondary as well. They're not clones. That being said, let's jump into some cases here. We're going to start off with the most basic case, which is we're going to choose our committee of 5 with absolutely no restrictions whatsoever. So we're just taking those people and choosing 5. Well, I am going to point out that if I put these all together, there are a total of 15 plus 11 plus 12, which is 38 people. Okay, so when we have no restrictions, we're not considering who's elementary, who's high school, and who's post-secondary. We're just considering them 38 individual people. So we should get 38, choose 5. And we're going to plug that into our calculator. And we're going to get out 501,942 possible groups of 5. Now, one thing I do want to point out, and this is fairly important here, is that since this is the unrestricted case, any restriction we put on this, anytime we say there's got to be something special about our group, it better come in as a number smaller than this. There's no way that putting a restriction on something can give you more options. You know, if I said go to the store and buy 5 objects, and you do, and then I say, okay, go to the store and buy 5 objects, but absolutely no potato chips, that shouldn't give you more choices. It gives you less choices. Okay, so let's keep that in mind that if we get a number greater than about 500,000, something is terribly wrong. Okay, part B. If the committee must consist of only high school students. Okay, this actually seems pretty easy. This just means that there are 11 high school students and we must choose 5 of them. Okay, so now if we calculate that out, we're absolutely right. The question is complete, but for the purpose of these examples, I'm going to write a little bit extra just to kind of get your brain to think a certain way. Okay, so bear with me for a second. Instead of just saying, okay, high school students, I need 5 of you, I'm also going to look at the elementary students and say, listen, people, we don't need any elementary students on this particular committee. Post-secondary students, we also don't need any of you. Sorry. Thanks anyway. So mathematically, what that would equate to is 11 choose 5 to choose 5 of the 11 high school. And then of the 15 elementary, we want to choose 0. And of the 12 post-secondary, we want to choose 0. Now, mathematically, anything choose 0 is going to be 1 because it's like, for instance, 15 choose 0 is 15 factorial over 15 factorial, 0 factorial. 15 factorials cancel. It's 1 over 1. We're good. So it's not needed for the mathematical answer, but what I want you to see is that we still are choosing from 38 people. If I look at those top 3 numbers, they still total 38. The bottom still total 5. So we're still choosing 5 out of 38. It's just we're restricting which part of the group we're taking from. And that kind of logic is actually fairly important. So I'm going to do these questions writing it this way, even though mathematically it's redundant. Mathematically, the only thing I have to punch into my calculator is 11 choose 5. And when I do that, I get 462 groups. By the way, I'm not going to keep reminding you of this, but at any point, if you would like to try these questions before you hear my explanations, please pause the video, try them, and then come back and see how you did. You may find that you do quite a bit better. And usually when I do this in class, I insist that students try these for about a minute each before we continue on. Okay, Part C, if it must consist of only high school students or elementary students, but not a mixture of both of them. So I can have 5 high school or 5 elementary, but I cannot have 2 of one and 3 of the other or anything like that. Okay, I'm going to kind of emphasize the word or there, because if you remember back, or tends to mean add, that we're looking at 2 different scenarios. We're looking at scenario 1, which is all high school students, and scenario 2, which is all elementary students. So to do this, if it was all high school students, we'd get the exact same answer we did above, but I'm going to write it out anyway. Or it's all elementary students, in which case we would say, high school guys, we need none of you, thanks anyway. 15 elementary, let's take 5 of you. And of the 12 post-secondary, we don't need any of you. Okay, the first one we already have a number for, that's 462. The second one, we can ignore the 2 choose zeros as far as our calculator is concerned and just do 15 choose 5, giving us 3003. So 3003 plus 462 is 3,465 possible groups. Now, I do want to point out that a fairly common incorrect answer to a question like this that I would see on a test is where people do mix the groups. They just say, well, there's 26 high school and elementary students. I'll just choose 5 of those 26 and no post-secondary, and then I'm done. And if you do that, the number is actually significantly larger because it includes a whole bunch of groups that have 4 of one, 1 of the other, or 3 of one, 2 of the other. Part D. The committee must have 1 post-secondary student, 2 high school students, and 2 elementary students. So here we're specifically prescribing how many of each group we need to take. And we treat it the same way that we treated the others. We say, okay, post-secondary students, there's 12 of you. I will choose 1. High school students, there are 11 of you. I will choose 2. And elementary students, there are 15 of you. I will choose 2 of you. Again, if you look carefully, the numbers on the top there still total 38. The bottom still, when you add them up, total 5. You are still choosing 5 out of 38 people. You're just breaking it down into kind of subgroups and choosing from each subgroup. This is an important logic idea that you need to understand when we're doing these. By the way, I think this is a good point now also to point out. I'm just going to zoom back to the last one as well. Why our new combination notation is a little bit nicer than the C bracket N comma R bracket. It turns out that permutations don't tend to come up in great numbers in single questions. You don't tend to have to use 5 permutations in one question, but a lot of combination questions you do. And if you wrote this out using the old notation, it becomes extremely long and hard to read. Whereas this notation, you can quite quickly see what's going on. Okay, so now again, I'm just going to point out that you can save yourself a little time. 12 choose 1 is just 12. I don't need to punch the whole thing into my calculator. Anything choose 1 is itself. You have 12 items, you're choosing one of them. That can happen 12 ways. So 12 times 11 choose 2. And usually I'll hit an equals between each one just to make sure that I'm not doing any weird bedmath stuff. And then multiply that by 15, choose 2. And I get 69,300. Hopefully I've done it correctly. Okay, part E. If the committee must have exactly 1 post-secondary student. Okay, so post-secondary students, there were 12 of those, so I'm going to choose 1. And I'm just going to point out a common mistake I see on this one is people who break it into cases where they say, okay, 1 post-secondary, and then there's going to be, 4 elementary, 1 no high school, or 3 elementary, 1 high school, or 2 elementary, 2 high school, or 1 elementary, 3 high school, or no elementary and 4 high school. And you could do it that way. It's just super tedious. The better way to think about this one is you've got 12 post-secondary. You want to choose 1 of them. And then you've got 15 plus 11 is 26 other people, and you want to choose 4 of them. And the other ones, it doesn't matter whether they're elementary or high school, so we don't bother differentiating the two groups. We just say of those 26 other people, we need 4. Again, tops total 38, bottoms total 5. So that's just going to be 12 times 26, choose 4. And I'm getting 179,400. All right, this next one usually confuses the crap out of people because I don't give enough explanation or they're making assumptions that aren't necessarily true. Okay, so if Lisa must be on the committee, now Lisa could be anyone, but I think if you look at the next few questions, you'll probably gather that I'm referring to The Simpsons. If you don't know who The Simpsons are, you don't need to. It's a television show. Lisa, Bart, and Nelson are all kids that go to Springfield Elementary. So we do know, or we can assume, maybe, if we knew this was The Simpsons, that Lisa's an elementary student. The question is, does that even matter in this question? So if you haven't given this one any thought yet, pause, give it some thought, because it's an interesting type of question. But when you're ready, we'll continue on. Okay, so does it matter that Lisa's an elementary student? And the answer is, for this question, no. And maybe it's just a coincidence that Lisa, Bart, and Nelson are the 3 names. Maybe one's elementary, one's high school, one's post-secondary. What matters is that the group is made up of Lisa and not Lisas. And in a group, I'm going to assume that Lisa is one specific kid, because I didn't say one of the Lisas, I just said Lisa. And what that means is we're going to break our 38 students into not elementary, high school, and post-secondary, but into Lisa and not Lisa. And the group of Lisa, which consists of 1 Lisa, we want to choose one of those. And the group of 37 non-Lisas, we want to choose 4 of those. So here's an example where, despite the fact that we already broke them into categories of elementary, high school, post-secondary, for this question, we're breaking them down differently. We're breaking them down by name. Lisas, not Lisas. 1 choose 1 doesn't do anything in your calculator. I just wrote it out there for logic's sake. So 37 choose 4 is 66,045. Part G is pretty similar. If Bart and Nelson must be on the committee. Okay, so now I'm breaking down the group of 38 into a group of Bart and Nelson and the group of 36 others. And of Bart and Nelson, I want to choose 2, and of the remaining 36 students, I want to choose 3. Again, you could do this in your calculator if you want, but anything choose itself is always going to be 1. There's only one way to choose everything in a group. So all we have to punch into our calculator is 36 choose 3, which is 7,140. Now, before we do part H, I'm actually going to look at part H and I together to see if we can recognize the difference between the 2 questions, because often students, despite the fact that these are different, treat them like they're the same situation. Okay, so if Bart and Nelson must not be on the committee, neither of them is allowed to be on the committee. That's one situation. And the other one is just Bart and Nelson must not be on the committee together. Now, we'll point out on a test, I won't actually add that last bracket of but either can be. I'll just say they cannot be on the committee together. And that's actually a different scenario. Okay, so for the first one, for H, Bart and Nelson must not be on the committee. The group of Bart and Nelson, we must choose neither of them. And the group of 36 remaining others, we must choose 5 of them. Again, 2 choose 0 is 1, doesn't do anything. 36 choose 5 is 376,992. Now, I'm just going to ask this to see if anyone's brain was thinking this way, despite the fact that I don't know what your answers are, because it's a video. But how many people kind of thought about this and said, let's do this indirectly and just do all the committees, the 501,000 or whatever it was, minus the 7,140 we got from they must be on the committee. The problem with that logic is that still allows for committees of one or the other being on it. It just doesn't allow both of them to be on it. So that actually method can work for part I. If either of them is allowed to be on the committee, they just can't be on the committee together, then what we can say is we can take all possible committees, and I know we have the number back in A, but I'm just going to write it down again anyway. In fact, before I write it down, I usually do this for indirect reasoning or multiple cases, but just to be clear, I'm going to do all minus both. So all possible committees minus the committees where both of them are together. And all possible committees is 52. I'm thinking deck of cards. 38, choose 5. Minus the result where they're both on the committee, and I'm not going to write down the combinations. I'm just going to look up above and say that it's 7,140. And same thing, I'm not going to bother writing out the number here. I'm just going to type 38, choose 5 into my calculator and get the 501,942. And then I'm going to subtract off 7,140. And I get 494,802. Okay, so that's how many committees can have, there can be made as long as both of them aren't allowed to be on the committee. Okay, I could also approach this one directly. The direct approach is looking for committees that have not both of them on the committee together. So I can do committees with none, neither of them, or I could do committees with just one. And if I do that, none of them, I actually just worked that out. That was part H. That was the 376,992. And then just one of them, I choose one of the two, and of the remaining 36, I choose 4 others. So I'm just going to punch that part into my calculator. 2 times 36, choose 4. And that's 376,992 plus 117,810. And now if I put those two together, hopefully I get the same answer. And together they total 494,612, which makes me question which number I maybe did incorrectly. Okay, after pausing the video and looking at this for like 4 minutes, I realized that I literally just made a calculation error. I think I hit the wrong button on my calculator for the very last step. If I actually, yeah, I checked every other number except for this one. If I actually put those together, I should really get 494,802. So those should be the same, and they are. Okay, so direct versus indirect reasoning, both of those work. One of them was a little bit less work. In this case, the direct was a little bit faster, especially since both of the numbers we'd already calculated. Whereas for the indirect method, the indirect method was faster because we had both numbers calculated. The direct method was a little longer because we hadn't calculated one of those numbers before, but pretty similar. 2 calculations either way. Okay, part J. If Laura, a high school student, must be on the committee and there must be 3 high school students and 2 elementary students. Okay, again, you may want to pause and think about this one. It may be slightly more complicated than you think, or maybe it's not. I'm not sure. You'll have to figure that out for yourself. All right, so here we're actually breaking down the groups into, there's a few things going on here. First, we have to break down the groups into LoRa. So there is a LoRa group, and we must choose one LoRa. And then there's the other high school students. The other high school students, there were a total of 11, so there's 10 left, and we have to choose 2 more from them so that we have 3 high school students total. And then the elementary students, we have 15 of them, and we need to choose 2. And again, this last number, much like the first one, it doesn't mathematically do anything, but I'm going to remind myself that there are, in fact, 12 post-secondary, of which we are choosing 0. So the first and last part of that, the 1 choose 1 and the 12 choose 0, do nothing mathematically, so we don't have to punch them into our calculator. But we do have to punch in the 10 choose 2 times 15 choose 2. And that gives us 4,725 possible groups. Okay, part K. There must be at least one post-secondary student chosen. I don't want you to write this next part down. I'm going to do it and then erase it because I want to show you the fault in the logic that is very common. So please be aware that what I'm about to do is going to yield the wrong number. Please understand that. Okay, so the incorrect but very common logic for this is I'm going to choose one high school or one post-secondary student. So I've got 12 post-secondaries. I'm going to choose 1. And now that I've chosen that one post-secondary, I'm going to let the other 4 be anyone from the group. If it's more post-secondary, fantastic. If it's not, that's okay too. So I'm going to say that there are 37 people left after I've chosen 1, and I'm going to choose 4 of them. And now when I do this, I'm going to punch into my calculator 12 times 37 choose 4. And I get out 792,540. Now, even if you kind of were okay with the logic in the question that I just did, or the way that I just did it, the answer should be a big red flag, because this answer is bigger than our unrestricted case. It's more than it was, like the 501,000 or 502,000-ish that we had unrestricted. Now we're up to almost 800,000. I want you to look carefully at these up here and see if you can see what seems to be wrong. What makes this different than all the other questions we've done so far? And hopefully you'll realize that the bottom totals 5, which is good, but the top does not total 38. It doesn't come out of our hole. The top totals 49, which is too many. So there's a big problem here. So here's one of the issues that we have. I'm going to try and draw this as a picture, and hopefully it will make sense. So let's say that one of our post-secondary students is Jim. Jim has spiky hair and a little smile. And so that's the one that we happen to choose as our post-secondary student. And then our 4 more, we're going to choose Pam. See if figure out where that came from. And she also has a little smile. And then plus 3 more people. Oops, I guess I should draw 3 more people. And it doesn't matter which those 3 are. So that's what happened. We chose one post-secondary student, Jim, and then we chose 4 more, and Pam, who's also a post-secondary student, happened to be in the group. Cool. Now, I could have a different scenario where I choose Pam as my one post-secondary student. And then in my other 4, by complete coincidence, I happen to get Jim. And Jim's having a worse hair day, I think, in that one. And doesn't seem to be as happy for some reason. Okay, so now let's say that the other 3 students happen to be the same in both of those scenarios. What happened here is that we're counting this as 2 different things happening. One where Jim is our post-secondary student with 4 others, and one where Pam is our post-secondary student with 4 others. And despite the fact that we're counting those as different groups, they are actually the same group. There's the exact same 5 people. And that means that we're overcounting, which is why this number is too big. So there's the flaw in the logic. So let me erase that and do this the correct way. Come on, erase all these little dots. I put too much hair on Jim, that's the problem. Okay, so here's the proper way of thinking about it. I can approach this, by the way, again, as a direct or indirect method. If I approach it, I'm just going to talk you through it first of all. If I approach it directly, then it would have to be 1 post-secondary student and 4 others, 4 non-post-secondary, or 2 post-secondaries and 3 others, or 3 post-secondaries and 2 others, or 4 post-secondaries and 1 other, or 5 post-secondaries. Those are all valid scenarios there to have at least 1. So that's going to be 5 cases that we have to work out if we do it directly. If we do it directly, we can do it as all possible cases, unrestricted, minus the cases where we have no post-secondary. And that seems like a much faster calculation, especially since we already actually have one of those numbers. So that first number is the 501,942. And then no post-secondary is 12, choose 0, no post-secondary students. And then we're going to choose 5 out of the 26 remaining students. So I'm just going to punch that all into my calculator at once. The 12 choose 0 does nothing. I'm just going to keep reminding you of things that do nothing or have no effect. So that's just 501,942 minus 26, choose 5. And that gives me 436,162, which is less than our unrestricted case, obviously, since we subtracted off from it, but I believe that's the correct answer. Now, at least it is the correct logic. Now, I'm not even going to bother writing out the direct logic. I kind of spoke through it just because it's actually quite long to even write out. It's a much, much, much longer solution. So we don't want to have to do that. Part L looks kind of similar. If there must be at least 2 high school students in the committee. So here we're going to actually think about this one again as direct and indirect. Direct would be 2 high school or 3 or 4 or 5. That's 4 possible scenarios. Indirect would be all minus the groups that have no high school students or just 1 high school student. That's 3 scenarios. And in this case, again, I think the indirect reasoning is going to be a little bit faster. So all minus 0 high school minus 1 high school. And again, you don't need to write out that description there. I just find it helps the logic, helps kind of the thinking process. And the all is the 501,942. 0 high school is 11, choose 0, and the remaining 27, choose 5. And then we have to subtract off 1 high school student, which will be 11, choose 1, and 27, choose 4. And this one I think is probably worth writing down these numbers individually just because I don't want to punch all that in my calculator and hope that I don't make a mistake. 11 choose 0 does nothing. 27 choose 5 is 80,730. And then 11 choose 1 is just 11 times 27 choose 4 is 193,050. Okay, so now I go back and punch in 501,942 minus 80730 minus 193,050. And I believe there are 228,162 possible groups that meet that criteria. All right, finally, we have reached the end of question 2 with part M. So I was wrong, there were only 13 parts, not 14, but whatever. If there must be no more than one elementary student. Okay, so now this one, again, we can look at our scenarios, and in this case, our direct reasoning is actually going to be faster because there's only two scenarios. We have no elementary or one elementary. We're just not allowed to have more than one. So we can have 0 elementary or 1 elementary. This, by the way, is probably the most realistic group. You never want too many elementary students on a panel, especially with, a bunch of older kids. Okay, so 0 elementary means that of the 15, we choose 0, and of the remaining 23 students, we choose 5, or 15 choose 1, 23 choose 4. So that first one, just 23 choose 5, is 33,649. And the second one is 15 times 23 choose 4, which is 132,825. And when I add those together, I get out 166,474. Okay. I think we've looked at every possible trick and everything that we could possibly get with choosing a group of 5 from those 3 groups. So we're going to move on and do one little last question. Okay, maybe not that little, but it's not too long either. We'll take a look at this one. I will confess I wrote this one when the first time I taught the first time I used this question in class was Halloween. But I've got a bag of 20 candies. I give 5 to my first period class, 8 to my second period class, and the rest for the last period class. Looking back, thinking I was really chintzy with the candy. I probably should have given out more than 20 pieces to 3 classes. But anyway, how many ways could I choose the candies to take to each class with him? So, well, with me, I guess, because this was about me. Anyway, so what that means is I'm going to take 5 to my first class. I've got 20 different candies to choose from. So that part seems easy. I've got 20 candies, and I'm going to choose 5. And above this, I'm just going to write down first, just to remind myself this is for the first class. And then I've got to choose second and last. Okay, just a reminder that I'm choosing candies for my first class and my second class and my last class, which means these are going to be multiplications, not additions. It's not an or. But what happens here is that I chose 5 out of the 20, and then I've got to choose 8 more, but it's not out of 20 anymore because 5 of them are already gone. They're in my first period class. So that means that I have 15 left to choose 8. And now of the 15, I've already used up 8 of them, leaving me with only 7. And I'm going to divvy those 7 out to my last class. Now, the reason I want to do a question like this is because it is different from all the ones that we did before this, because you'll notice that the bottom does total 20, but the top does not total 20. The reason that it doesn't have to is because I'm actually not choosing to break down the things into 3 groups. And choose from each group. I'm choosing some for one group, and then I'm using what's left over for the next and what's left over for the third. So these ones, they don't follow that rule of the tops have to total the total and the bottoms have to total the total that you're choosing. So now if I do this, I can punch this into my calculator. I'm going to try and do it in one step and hopefully get it right. 20 choose 5 times 15 choose 8 times 7 choose 7. And if I was smart, I would have realized the 7 choose 7 is just 1, so it doesn't do anything. And the final answer, if I get the right number of spaces here, is 99,768,240. So just splitting 20 candies between 3 classes, I have almost 100 million possible options. That's crazy. It's crazy it could be that many, but it is. So now that's the answer to the question, and technically we're done, but I want to actually look at two little separate things that go with this question because both of them actually give some insight into what's happening. The first thing is, what if I chose my classes in a different order? What if I chose the candies for my last period class first, and then my second, and then my first? So if I do that, you'll notice that the numbers don't turn out to be the same. It's not just a switching of the order of those combinations, it's actually different combinations. So if I choose the last class first, I have 20 candies and I choose 7 to take there, leaving me with 13 candies for the second class, and I have to choose 8. And then the first class, I have to choose 5 of 5. So those are completely different combinations than I got in the first one, but let's see if they actually work out to be the same thing. So 20 choose 7 times 13 choose 8. And again, I'm not going to punch in the 5 choose 5 because that's just 1. And I get out 99,768,240. Okay, good news is it's the same answer, which it should be. Which group I choose first shouldn't affect the number of choices I have, despite the fact that it gives different numbers. So what I want to do is just show you that with both of these, what happens, I'll do it for the first grouping, just because I choose to. But if I do it for the first grouping, if I broke this down into its factorial definitions, 20 choose 5 is 20 factorial over 15 factorial 5 factorial. And then 15 choose 8 is 15 factorial over 7 factorial 8 factorial. And 7 choose 7 is, well, it's boring, but 7 factorial divided by 7 factorial, 0 factorial. I think I did those in the opposite order, but again, doesn't really matter which one's first. 0 factorial and 7 factorial on the bottom. Now something interesting here happens. There's a 15 factorial on the bottom and the top. The fact that they're in different fractions doesn't matter since they're all multiplied together. There is a 7 factorial on the top and bottom there. The 0 factorial I'm just going to cross out because it doesn't do anything. It's just 1. And what I'm left with after that, I think, I hope, is 20 factorial on the top and 5 factorial, 7 factorial, 8 factorial on the bottom. 20 is the number of candies I had. 5, 7, and 8 are the number of candies I'm taking to each of the 3 classes. And the order of those multiplications doesn't matter. So whether I'm doing 5, then 8, then 7, or 7, then 8, then 5, or 8, then 7, then 5, or 5, and 7, and 8, or any of those, it's always going to yield that exact same answer. So this part is always going to be true when I simplify it, including for this version right there. So it doesn't matter which order I choose candies for the classes, I'm always going to get that answer. Okay, one final detail I want to point out, just in case people are wondering why this equation at the bottom works. Because this equation here, right there, looks a lot like I have 20 different things, and then I have 5 of the same, 7 of the same, 8 of the same. So if you remember back when we were doing permutations with words and we had repeated elements in them, we said, okay, it's going to be the number of things factorial divided by the number of repeats factorial, the 5, in this case, 5, 7, and 8. However, the candies aren't different. So why does this equation work? Like I don't have 5 identical candies and 7 identical candies and 8 identical candies, which would then kind of make sense. They're all different. Why am I dividing it like they're identicals? And the answer is, while the candies themselves aren't identical, the classes are. So the 5 going to the first period class, I can consider them all to be identical, not the candies, but the fact that it goes to the first class, 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 goes to the first class. So I could think of this as saying, here's my 20 candies. The first 5 are going to the first class. The next 8 are going to the second class. and the last 7 are going to the last class. So that would be choosing the first 5 candies for the first class, then the next 8, then the last 7. But I can rearrange the order of that any way I want. I could take the first and the 8th and the 15th candy to my first class. And because I can rearrange that word, I can do it in 20 ways with 5 firsts, 8 seconds, and 8 S's and 7 L's, which is why that equation turns out to work. So what seems like a completely different problem than our words with identical letters, which was actually a permutation logic, it seems to work just fine here. Okay. I think I'm going to stop there, mostly because this has been a really, really long lesson. And I got to give you some time to try these ideas out on questions. Now, if you get it wrong the first time, don't freak out. Just remember that there's some real subtle logic differences between questions. If we think of like the Barton Nelson type questions, etc. So before you give up, look at it and see if you can find a flaw in your logic. And I will confess that as a student, I found that very, very difficult. So I understand if you're struggling. But try some of the questions. It's the only way you're going to get past kind of seeing or not seeing the logic in these. And then if you've got questions, let me know and we'll see how we can, what we can do to fix that. Okay, I'm going to stop here and I will see you in the next lesson.